So this will be the 6th lecture over NMR spectroscopy. So in this lecture, the main thing we'll cover is how chirality affects NMR. Okay, so first let's do a little refresher. Remind yourselves of some of the basic principles of chirality. So if we take these two molecules drawn, right, you have a carbon atom with 4 different things attached. So it's a chiral carbon, and it's a mirror image, so sketch its mirror image, so it's a mirror image, they're not superimposable on each other. So those two molecules would be enantiomers of each other, and if you remember, enantiomers have exactly the same physical chemical properties. Their only difference is how they rotate plane polarized light and how they interact with other chiral molecules. So it has 1 chiral carbon, so if you remember this formula, 2 to the n, where n's the number of chiral carbons. So 2 to the 1, so that means this molecule would have 2 stereoisomers, the R and the S isomer, which are the 2 stereoisomers drawn. If we take a molecule like this with 2 chiral carbons, right, so both of these carbons are chiral, they both have 4 different things attached. So if there's 2 chiral carbons, then 2 to the 4, there's 4 different stereoisomers. So let's draw the other 3 stereoisomers. So the easiest thing to do, so if we keep one of these chiral centers the same, and then we switch 2 groups on the other, so if we put the bromine on the solid wedge and the hydrogen on the dashed wedge, then that would create a different stereoisomer. Or we could keep the bromine and hydrogen the same, and we could swap the hydrogen and the OH, so that would be a different stereoisomer. Or we could swap both chiral centers, so if we swap the OH and the H and the bromine and the hydrogen, then that would be the 4th stereoisomer. So then what's the relationship between these two? So if we compared 1 to 2, so 1 chiral center is the same, but 1 chiral center is opposite. So those 2 molecules would be diastereomers, right? So to be enantiomers, every single chiral carbon has to be changed, has to be opposite. So if we compared 1 and 3, well, this is opposite, but we switch the H and the OH. If we switch 2 groups, that changes the stereochemistry. And this is opposite, right? No, that's the same. So 1 and 3 would be diastereomers. And if we compared 1 and 4, that's opposite of 1, and that's opposite of 1. We swap both of those, so 1 and 4 would be enantiomers of each other. And then similarly, if we compared 2 and 3, so the OH and H has been flipped, and the H and the Br has been flipped, so 2 and 3 would be enantiomers. So 4 stereoisomers, there's only 2 pair of enantiomers, so all of the other relationships are going to be diastereomers of each other. Okay, so hopefully you remember that. If you don't remember that, you can go back and watch my videos over Organic Chemistry 1, Stereochemistry. Chapter 5, that would be chapter 5. Those videos over chapter 5 is over chirality. Okay, so you just need to know the basics for this NMR. So one thing that we want to do is be able to classify hydrogens as being homotopic and antiotopic or diastereotopic with respect to each other. So if we take this molecule, HA and HB, and what's the relationship between those 2 hydrogens? So the way to figure this out is to take HA and HB and swap it out with something else. So replace it with something else. So if we take HA and swap it out, and let's just put a deuterium there. Doesn't matter what you put there, anything but hydrogen. Or if we take HB and change it out, and if we put a deuterium there, for example, now if we compare these 2 molecules, what's the relationship between them? Are they the same? Are they enantiomers or are they diastereomers? And these 2 molecules you could see are the same. If you just flip this molecule over 180 degrees, then the 2 molecules would superimpose on each other, so they're the same molecule. So HA and HB then are said to be homotopic. So if the 2 molecules are the same, then HB and A and B are homotopic, and hydrogens are exactly the same. They will not split each other in proton NMR. And that means then also that the CH3s would split with HA and HB exactly the same. So the CH3s would simply be a triplet. 2 neighbors, HA and HB, 2 neighbors, 3 peaks, triplet. Okay, so if we take this molecule where we've changed the CH3, one of them, to a CF3. So now if we do the same, if we swap out HA or swap out HB and put something else there like deuterium. So now are those two molecules the same, or are they enantiomers, or are they diastereomers of each other? Well, so now these molecules are not the same, right? If you flip them over 180 degrees, the hydrogens and deuteriums line up, but then the CH3 and the CF3s don't line up. So these molecules have one chiral center, and the chiral center is opposite because we swapped 2 groups, so they must be enantiomers of each other. So HA and HB then are said to be enantiotopic. So what we want to do now is classify. So one of them is what's called the pro-R isomer, and one of them is, or the hydrogen, one's called the pro-S hydrogen. So if we assign stereochemistry here, for example, so if you remember how to do this, that's carbon number. So that would be priority 1, that's priority 2. Deuterium has a higher mass than hydrogen does, so that's 3, and hydrogen's 4. So 1 to 2 to 3 is counterclockwise. Counterclockwise is S. 4 is in the back, so the arrow remains counterclockwise. So if we swap out HA, we get the S isomer. So this is called the pro-S hydrogen. And for this one, so that's priority 1, 2, 3. 1 to 2 to 3 is counterclockwise, that would be S, but 4 is in the front. So we would reverse the arrow, so that's R. So then B, if we swap out HB, we get the R isomer, so this is the pro-R hydrogen. But the point is they're enantiotopic. So if the 2 resulting molecules are enantiomers of each other, then the 2 hydrogens are said to be enantiotopic. And so one is pro-R, one is pro-S, but enantiotopics, the main point is that enantiotopic hydrogens are in the same magnetic environment, and so they do not split each other. So here the CH3 would split with HA and HB exactly the same, so it would just be 2 neighbors, so CH3 would be a triplet. And the 2 hydrogens, HA and HB, would simply see the CH3, 3 neighbors, so 4 peaks, but they would be quartets. So the simple n+1 rule works. Okay, so if we take this molecule, so now if we do the same, so HA and HB, so let's change HA and let's change HB for something else. So if we put deuterium here and then compare those 2 molecules, so that's a chiral carbon, so the same, nothing's changed on that chiral carbon, but this one is opposite, right? H and deuterium have been flipped, so one chiral center is the same, one chiral center is opposite. These 2 molecules therefore must be diastereomers. So HA and HB are said to be diastereotopic. Okay, so the significance of this. So if the 2 resultant molecules are diastereomers, then HA and HB are said to be diastereotopic. One is still pro-R, one is pro-S. That doesn't really matter to this discussion, but what does matter is that diastereotopic hydrogens are in different environments and they can split each other. So HA could split with HB, so it's like having another neighbor. But it's more complex than that, so we'll go through some splitting tree diagrams in a little bit to show you what that spectra could look like. So why are HA and HB in different environments? So if we drew a Newman projection, so if we were standing here and looked at the molecule from this perspective, if you remember how to draw Newman projections, so we would see the carboxylic acid towards your head, and then this would be towards your left foot, and this would be towards our right foot. So that's how they end up here, left, right, feet, and this is towards your head. And then in the back carbon, this would be towards your left hand. Since it's on the solid wedge, it's coming out. So this would be in your left hand. This would be on your right hand. So it's on the right side. So left and right side in the Newman projection, and this is towards your feet. So with CH3 is on your bottom. Okay, so if we look at this molecule from a Newman perspective, then we can see that HB is in a different environment than HA, because HB is between the carboxylic acid and the hydrogen, and HA is between the carboxylic acid and the NH2. Different environments, so those protons will, the CH3 would split differently with them, and they will split with each other. Okay, so HA and HB are always different. Doesn't matter how you rotate this Newman projection. So if we just rotate around this carbon-carbon bond, so if we rotate around this bond and try to see, can we put HA and HB in similar environments or not? And the answer is no, there's no way to do that, no matter how you rotate this. So if HB is between the carboxylic acid and the hydrogen, then HA is between the nitrogen and the carboxylic acid. Well, so if we put HA between the carboxylic acid and the hydrogen, then HB is now between the NH2 and the H. So, right, so when that's between carboxylic acid and hydrogen, HA is in a different place than, whereas if HA was between carboxylic and hydrogen, HB is not in the same place that HA would have been. So they're different. They're always in different environments, and so that means they can split each other. So there's a coupling constant between them. So if we contrasted that to these enantiotopic hydrogens, if we did the same thing, if we looked at the Newman projection from there, so we have hydrogen towards our head and left and right foot, and then HA towards our left hand, B towards our right hand, and CF3 towards our feet. And so you can see that HA and HB are in the same environment. They are both between two hydrogens. So they're equivalent, so they're not going to split each other. And so it doesn't matter if there's something else here, if there's a CH3 there, right? This is still not a chiral carbon. So HA and HB are still enantiotopic, and you can see if we drew a Newman projection, HA and HB are still in the same environment. So they're not going to split each other, because equivalent hydrogens don't split each other. Okay, so that's just another example of a diastereotopic hydrogens, where you can see that HA and HB are in different environments. Different hydrogens can split each other. Okay, so now it depends on what the coupling constants are. So if we looked at HA and HB, right, so they're different, so they can split each other. And then they can split with CH3, and they can split with the hydrogen. So if all of the coupling constants are the same or very, very similar, and your NMR doesn't have good enough resolution, then the simple N+1 rule would work. So then CH3 and H, so that's 4 neighbors, so that would be 5 peaks. So HA and HB would be a pentet. That's if all of the coupling constants are very similar or the same. But if the coupling constants between HA and HB is different than it is between the CH3 and the CH3 neighbor, then the simple N+1 rule does not work. And so in this case, you would see separate signals for HA and HB, and you would have to use a splitting tree diagram to figure out what the splitting pattern is going to look like. So let's go through that. Okay, so if the coupling constant between A and B is significantly different than the coupling constant between with the CH3, or the coupling constants between those hydrogens and the CH. So the geminal coupling constants are the biggest. So A is going to, so if we just focus on A, so A is going to be split by B. So that's like one neighbor, so 2 peaks. So JA is split by HB into a doublet. And now let's say this coupling between A and the CH3 and A and the CH, let's just call that hydrogen C. Let's call those coupling constants very similar. So then you're going to see 4 neighbors, so 5 peaks. So So this peak and this peak then would then be split into 5 peaks, and now you would see a doublet of pentets. Okay, so now if the situation was opposite, if the coupling constant with CH3 and H was bigger than the coupling constant with HB, then you would do that first. So then you would split with the CH3 and the CH first, so that would be a pentet. And then those 5 signals would be split by HA into doublets, so then you would have a pentet of doublets. Right, so the main point being the proton NMR of chiral molecules can be very complex if diastereotopic hydrogens are present. So usually the N+1 rule is not going to work. So the same would then be true for the CH3 and the CH. So the CH3 has 2 neighbors, HA and HB. So you might think, okay, 2 neighbors, it's going to be a triplet, but it's not. It's not going to be a triplet. So what would the CH3 look like? So it would be split by HA or HB first. So let's just say it splits with, so this is the CH3 to A. So that splits into a doublet, one neighbor, 2 peaks. And then each of those peaks would be split by HB. So the CH3 then would actually be a doublet of doublets. And then the same would be true for HC. So HC, there's 2 neighbors there, but those 2 neighbors are not equivalent to each other. So HC can split with them separately and differently. So HC would split with HA, for example, into a doublet, and then HB would split each of those peaks into a doublet, so then you would have a doublet of doublets again. Okay, so let's take this molecule. So are those 2 hydrogens homotopic and antiotopic or diastereotopic? So again, so let's just replace HA with deuterium or HB with deuterium, and if we compare those 2 molecules, that is now a chiral carbon, but those 2 molecules are enantiomers of each other, right? Only one chiral carbon, and the 2 chiral centers are opposite of each other, so they're enantiomers, so these 2 hydrogens are enantiotopic. And the same is true for HC and HD, they're enantiotopic. And so enantiotopic, so if they're enantiotopic, then the N+1 rule works. So HA and HB have 2 neighbors in C and D. C and D are equivalent, so they're going to split HA and HB the same. So it's just going to be a triplet. So you would just see 2 triplets in this molecule. Right, which triplets further downfield? Well, this would be HAB, right? Because it's closer to oxygen, so it's going to be further downfield. Right next to C double bond O gets you about 2 ppm, and this would be HCD. Okay, how about this molecule, these 2 molecules? So now if we have HA and HB, so again, if we swap out HA and HB for deuterium, and if we compare those 2 molecules, since there's already a chiral carbon in the molecule, right, this is the same. But for this chiral center, it's opposite. So here, A and B would be diastereotopic. All right, so what does that mean? So if we call this HC, and then if we bring in these hydrogens over here, that means since HA and HB are diastereotopic, HC can split with them differently, so it would probably be a doublet of doublets. And then HD and HE can also split with HA and HB differently. So the spectra would be much more complex than the simple N+1 rule. Okay, so for this molecule, if we swap out HA and HB for deuterium, then these 2 molecules are the same molecule, right? We can just flip it over like that, and everything superimposes. So these are homotopic. So N+1 rule works. And you would expect to see they have 4 neighbors, so 5 peaks, a pentet for HA and HB. I guess it can technically be a little bit more complex than that because it is a ring and you don't have free rotation. And so by adopting an envelope conformation, you can put HB and HA in different environments. So in ring compound, actually, your spectra will probably not quite so simple as the N+1 rule, because HA and HB could exist in different environments. So it all depends on, if you remember the envelope conformation, right? It all depends on how fast those interconvert between each other, whether they would interconvert fast enough that the NMR would see them as being equivalent, or if the interconversion was slow like a cyclohexane chair flip, then they could be different and the NMR could see them as being different signals. Okay, so let's take an example, throw in some coupling constants. So if we take this molecule, so this is phenylalanine, an amino acid, so HA and HB. So since we have a chiral center there, then HA and HB are going to be diastereotopic, right? So A and B can split each other, and hydrogens on the same carbon that are not equivalent to each other. So it's this 2-bond coupling, right? 1 bond, 2 bonds. They're on the same carbon. They're 2 bonds away from each other, and that 2-bond coupling is about 13 to 14 hertz. So A and B are going to split with each other. And they're going to split with HC because HC is a neighbor as well, right? But the coupling constants are different, so it's not going to be a simple N+1 rule. You're going to have to use a splitting tree diagram to see what it would look like. So if you did this on a 300 megahertz NMR, though, where you don't have as good resolution, so if we were looking at the, so this would be for HC. It's got 2 neighbors, HA and HB, so it would be a triplet, right? And HA and HB would just show up, well, or HA has 2 neighbors. It's got an HB neighbor and an HC neighbor, so 2 neighbors, 3 peaks, triplet. But if you did this on a more powerful NMR, like a 500 megahertz NMR, we have better resolution. So if we just go through this for HA, so HA is going to be split by HB. So 1 neighbor, 2 peaks, so a doublet, and the coupling constant's about 14 hertz. So those 2 peaks would be 14 hertz apart. And then HC, one neighbor, is going to split each of those peaks into 2. So you're going to have a double of the doublets. And this coupling, whoops. So this coupling's around 7 hertz. Okay, so that's going to be split into 7 hertz. And if we try to figure out what the distance is between the inner 2 peaks, so that's going to go 3.5 hertz this way and 3.5 hertz this way, right? So it went 7 hertz. So from the HA, so the middle, it went 7 hertz to the left, and then you come back 3.5, and then it went 7 hertz to the right, and then you come back 3.5. So the distance between the inner 2 peaks would be 7 hertz as well. So you would see a double of the doublets, where you would have, in this case, just because of the way the coupling constants, the magnitude of them, you would have 7 hertz, 7 hertz, and 7 hertz between all of those. So again, it's 4 peaks, but it's not a quartet, right? How do you know it's not a quartet? Because a quartet comes in a 1 to 3 or 3 to 1 ratio, and those peaks are in a 1 to 1 to 1 to 1 ratio. Okay, so the NMR for this molecule would look something like this. So the OH, or the carboxylic acid, down around 11 to 12 ppm. Right, your benzene hydrogens would be around 7 to 8 ppm. Your NH2 hydrogens would be a broad singlet, so anywhere from 1 to 5 ppm typically. And then you would see this little signal if you're using chloroform as a solvent, if you're using 99.8% CdCl3, right? Well, there's 0.2% CHCl3 there. So you would see a signal for that hydrogen, so that would be around 7.2 ppm. And then HA, HB, and HC are all going to be double of doublets. So how would you know which one is which? Well, chemical shift would help some. So this hydrogen is on a carbon that's next to nitrogen, so it's going to be the farthest down filled. And then in terms of HA and HB, You could use coupling constants to try to figure out which one was which, would be one way, but they're all going to be doublet with doublets. And next to benzene ring is going to get you around 2 to 3 ppm. Okay, so if we took a molecule like this, so just to illustrate how complex a chiral center can make things. So if we took HA, B, C, D, E, F, G, H, they are all diastereotopic hydrogens, right? Because if you replace A and B with deuterium, that creates another chiral center. If you replace C or D with deuterium, that creates another chiral center. Same for E and F and G and H, they're all diastereotopic. So technically, even way out here, G and H could technically split with each other. But obviously the further away from a chiral center, the more similar hydrogens become. So you would most likely observe the chiral effect at A and HB. Maybe you would observe it at C and D. Although if you had a powerful enough NMR that could resolve really close coupling constants, you might see it farther away from the chiral center than that. Or it all depends on, of course, too, the conformation that the molecule adopts. If it adopts the conformations that puts things in close space to each other, then that can affect the splitting pattern. Okay, so I think this is the last example. There's where we kind of dive into what the splitting would look like. So just that's another example to illustrate how complex it can be. So if we just took HA, so HA is going to split with H1, it's going to split with HB, and it's going to split with C and D, all right? So now it all depends on what the coupling constants are, as to what the spectra is going to look like. So if the AB coupling constant is the biggest, but let's say then it splits with H1 and C and D similarly, then you would see a doublet of quartets, right? It splits with B to a doublet, and then you have HC and D and H1, 3 neighbors, 4 peaks, so that doublet would be split into 2 quartets. Right, or let's see, in this scenario what we have is it splits, so the coupling with CD is smaller than the coupling with H1, which is smaller than the coupling with HB. So it splits with B first into a doublet, and then if the coupling with H1 is larger than the CD, then H1 would split each of those doublets into doublets. And then if it splits with HCD, that's 2 neighbors, 3 peaks, it would split each of those doublets into triplets, so now you would have a quartet of triplets. Right, or another possible scenario, so AB geminal is the biggest, so but maybe it splits with CD, maybe that coupling is bigger than with H1, so B splits it into a doublet, and then CD, 2 neighbors, 3 peaks, each of those doublets is split into a triplet, and then it splits with H1, 1 neighbor, 2 peaks, so each of those triplet peaks then is split into a doublet, and now you have a sextet of doublets, right? And most likely, so probably what you would end up with is just a mess. You would end up with a multiplet. Unless you had really good shimming and really good resolution, you probably could not see all of these peaks. You would just see kind of a mess, right, that you would just call a multiplet. So you've lost some information. If you can't interpret the multiplet, then you can't figure out how many neighbors it has. But again, that's all going to depend on how good the shimming is and how good the instrument, how powerful the magnet is, how good of resolution you have, whether you can resolve all of these signals or not. Okay, so if we take this molecule, HA and HB, are they homotopic, enantiotopic, or diastereotopic? Well, so right now, so the molecule I was drawing, this carbon is not chiral, right? Because you have an oxygen and then CH2, CH3, oxygen, CH2, CH3, so there's no chiral center in the molecule. But if we replace HA with deuterium or HB with deuterium, so now that carbon is chiral, right? But now that carbon is also chiral. So now you have 2 chiral carbons in the molecule. So these two hydrogens are then diastereotopic. Right, so the point is, if replacing two hydrogens creates chiral carbon on that, it's always going to, well, it's not always, if it creates a chiral carbon on the carbon where HA and HB is at, and it creates another chiral carbon in the process, then those two hydrogens are going to be diastereotopic. So then HA could be split by HB into a doublet, and then each of those peaks with three neighbors, 4 peaks, each of those doublets could be split into quartets, so you could see a doublet of quartets for HA and HB. So HA would be a doublet of quartets, and HB would be a doublet of quartets. And if they had different enough environments, then those two doublet of quartets would be separate. If their environments were similar, then those doublet of quartets could be overlapping each other, and you would have a mess. Okay, if we take this molecule, so it's got a chiral carbon in it, right? So use this to illustrate the point that these two methyl groups are diastereotopic. So you can have diastereotopic methyl groups just like you can have diastereotopic hydrogens. So if we took this molecule, for example, and drew a Newman projection looking down that carbon-carbon bond, so we see this methyl on our head, this is on our left foot, this is on our right foot, and then the two methyls in the back would be on our left and right hands, and this hydrogen would be towards our feet. So if we do that, then you can see that this CH3 is between a methyl and a hydrogen, whereas this CH3 is between a methyl and an OH group. So they are different. They are in different chemical environments, which means they can give distinct signals. So you might normally say, okay, this is going to be a doublet for 6 hydrogens. So normally you might say it'd be a doublet that integrates to 6 hydrogens, right? That's if the simple N+1 rule works, but if you recognize that these methyl groups are different, they're diastereotopic, then that doesn't apply. Right, so you can see that they're diastereotopic if we replace the CH3 with the CD3, and if we compare these two molecules, right, this is the same. But this chiral center is now opposite. So that's now a chiral center, so those are diastereotopic methyl groups. Okay, so what would the NMR of this look like? So this CH3 is easy. It's just got that one neighbor, so it's going to be a doublet. So it's and it's going to be the farthest downfield because it's closest to oxygen, so that would be a doublet around 2 ppm. But these other two CH3s, they can have their own separate signals. So this CH3 has a neighbor, so it would be a doublet, and this CH3 has a neighbor, so it would be a doublet. So you could see 2 different doublets for the 2 methyl groups, and then they would independently integrate to 3, right? So that would be the situation if you had a difference in chemical shift between them. Or you could find that the chemical shifts were similar. So I've drawn them here to illustrate that this inner peak, for example, could be at the similar chemical shift. And so now if we took those and superimposed them on each other, then it looks like a triplet integrated to 6. And then that could be deceptive. You could say, okay, a triplet needs to have 2 neighbors, but it doesn't because it's not really a triplet. How do you know it's not a triplet? Because a triplet's in a 1 to 2 to 1 ratio, and that's not a 1 to 2 to 1 ratio. So there's subtle clues like that that you have to look for that would help you figure out what the multiplicity of a signal really is. So this is really just it's 2 overlapping doublets. Right, that have their inner signal overlapping. Okay, so just to summarize that in terms of at least picking out homotopic and antiotopic and diastereotopic hydrogens. So if R1 and R2 is the same, then HA and HB are homotopic. So yes, so if R1 and R2 do not have a chiral carbon, and if substituting HA and HB does not create a chiral carbon in R1 or R2, then But if R2 is not the same as R1, so here R1 does not equal R2, and if substituting HA or HB does not create a chiral carbon in R1 or R2, then HA and HB are enantiotopic. Right. But if R1 or R2 has a chiral center, and substituting HA or HB creates a chiral carbon, then HA and HB are diastereotopic with respect to each other. So that's something you always have to look out for when you're doing NMR, is whether it's you have diastereotopic hydrogens or not, because that's going to complicate the NMR. Okay.